Okay, so hello everyone. So my name is Alexandre Morin from Noveltis, and I will be presenting you this Jupyter notebook on climate change. So today's topic is climate change, and this particular Jupyter notebook will be focused on temperatures and droughts. So of course, climate change is a topic that you cannot avoid nowadays, especially when you study science. So as you know, it's mainly driven by human activities with the emission of greenhouse gases. And so we can already observe that it's already altering the precipitation patterns, temperature patterns, the frequency of extreme weather events, for example. And those changes are not necessarily happening all in the same way around the globe. And so this is what is crucial to understand and try to make predictions about future climate in order to anticipate possible mitigation policies, etc. So as I've mentioned in this tutorial, we are going to see the evolution of temperature and droughts. And for that, we are going to use climate simulations, which I'm going to present you in the next section. And the simulation will follow several different scenarios. So if you're already familiar with climate science, maybe you're familiar with the term RCP, which is a representative concentration pathway. So basically, those represent different scenarios of greenhouse gas emissions, going from 2.6, which is a scenario where climate is so where greenhouse gas emission have been very mitigated, and to the RCP 8.5 scenario where no efforts has been made to mitigate climate change. So it's a best case to worst case scenario basically. And so climate simulation have been made under those several scenarios, and this is what we're going to see. What are the impacts in terms of temperatures and precipitations? So I found this little graph here about different scenarios. So this is a summary of what I've explained to you. So 2.6 is a high effort on mitigation of global warming, and 8.5 is the worst case scenario with other scenarios in between. Okay, so this notebook works with Python. So if you're already familiar with Python, there are a number of libraries here that you probably already know. We are using NumPy, which is fundamental for processing Python arrays. Xarray is the most commonly used Python library to process netcdf data, which is the format in which the climate projections come. Matplotlib and Cartopy are used to draw the different maps and plots that we're going to draw in this notebook. GeoPandas is used to read and process geospatial vector data. So we chat geometries. And Rio Xarray is an extension of the Xarray library. It will allow us to combine the netcdf data to geometric datasets in order to crop the data to a certain area of interest, for instance. And so to use all of that, we recommend to use the WEkEO lab kernel because it is here, because it has all those libraries already pre-installed. And one more thing is that in this notebook, so we are going to use climate prediction from the ECMWF platform. So it's available through WEkEO, but the original platform is this one. And to retrieve data from there, we can first use the traditional harmonized access API that David presented you before me, or the EarthKit library, which allows us to access the data in a more practical way. So this is not pre-installed on the WEkEO lab kernel. So to have it installed, just follow this procedure here. So you just open a terminal. Take some time, yeah. And then enter those two commands to activate the environment and to install EarthKit within it. And that way, you will be able to import it in the notebook. So there is a dedicated article on EarthKit on the WEkEO website. So please feel free to visit it if you want to know more about how to use this particular library. So on my side, I've quite followed the same instruction. So setting up the cache for EarthKit. And afterwards, you will see how it works because I'm going to show it to you in detail. So to access the data, so I've already mentioned the library. Here is a brief overview of the products that we're going to use. So as I've mentioned, we are going to use climate simulations. So we're going to have monthly data. Sorry, depending on the section, we're going to have monthly or daily data. For the monthly data, we're only going to use temperature. So it's temperature at surface. And for the daily data, you will see that we will use temperature and precipitations. So both of those datasets are available on WEkEO. So here's the dedicated page on the viewer, for example. Oh, I'm not logged in, so it probably hasn't displayed it the way, well, it doesn't, it's not, it's not that serious. So, okay, so it's available on WEkEO. And we have monthly and daily data, both covering different periods. So we'll see how they are important. But basically, we're going to have an historical data set that will serve as reference and two projections going from 2006 to 2100 for the monthly data and 2056 to 2100 for the daily data. So now, in order to retrieve the and also, if you want to know more about what models are used and in which context, well, there are dedicated pages on the ECMWF website, which will explain to you in detail where those datasets come from. Okay, so now in order to retrieve the data, here's a brief overview of how I use the HDA API, which was presented by David in the previous presentation. So in this cell, it is just to set up your credentials in the .hdrc file. So if you already have one, this cell will not do anything. But if it's your first time using the HDA API, you might need to enter a credential that way. And then, as explained by David before, I have set up data request files in the JSON format by copying and pasting it from the WEkEO data viewer. So for instance, here, I can retrieve, for example, set up this request with the identifier of the monthly dataset of climate projections. Here is the climate scenario that I have that I want to retrieve. So RCP 4.5. I'm retrieving the 2-meter temperature. Here is the model that I've chosen, the number of the simulation and the period, so 2006 to 2100. So this is quite what we were expecting. And using the traditional harmonized data access method, you can just, load this data and load it with the HDA client. And you can see that it has found one item, and then you can download it. So as we are working with climate data and we have several decades of data, I'm not executing the cells live because it would take quite some time. So I'm just going to go on. And then using EarthKit it's almost the same procedure, meaning that we use the same data request files in order to use EarthKit. So you can see that we still load the same dataset here. But this time, using the from source function from the EarthKit library, all we need to do is to enter the service that we're using. So it's WEkEO, the ID of the dataset. So it's still a projection on monthly single levels, and well, our data request file as an argument. And the difference here is that instead of downloading the data in your Jupyter, in your WEkEO user space, it will only download it in a cache and allow you directly to store the data in a variable and use it immediately as an X-array within the notebook. So here I've downloaded it using EarthKit. So I'm going to keep going because, well, it still takes some time to download. And here is the dataset that I've downloaded using EarthKit. So it's the temperature from the RCP 4.5 scenario. So you can see that it has several dimensions. So latitude and longitude, this is something that we were expecting, and time also. So you can see that time goes from here, January 2006 to December 2100. So this is consistent. Latitudes go from, well, it covers all the latitudes from minus 90 degrees to 90 degrees. And from longitude, they go from 0 to 360. And we have some other dimensions here, like this bounds dimension, and also in the variables, time bounds, lat bounds, land bounds that we are not going to use. And we're going to drop them because, well, it might yield errors in the future processing. And here is the temperature data. So you can see that it's a long time, latitudes and longitudes. And here is some metadata that you can read if you want to know more about the dataset. So in this first section, what I do here is that I show the evolution of temperature under the RCP 4.5 scenario. So basically what I do here is the pre-processing to drop the variables I've told you about. Here I wrap the longitude to shift them from 0 to 360 to minus 180 to 180 degrees, because it will be more convenient to work with than with Python and Matplotlib. And here I basically do a special average of the temperature data in order to have the global evolution of the temperature over time. And this is what the dataset yields, so from 2006 to 2100. And you can see that under this pathway, so RCP 4.5, we have a clear increase of the temperature over a century. So this is the result for one scenario. But let's compare it to the other scenarios that I've shown you before in this graph. So the 2.6, 6.0, 8.5, and see how the different scenarios evolve. So here you can see that I'm retrieving data using EarthKit once again, so with the same method, and I have written one request file for each of the scenarios using the same dataset, the same model, the same experiment number. They are all here available. I'm performing the same weighted spatial average here along the longitude and latitude dimensions. And then when I plot all the data, you can see that depending on the scenario, the evolution of temperatures is quite different. So here in RCP 2.6, you can see that we have a clear stabilization around 15 degrees on the global level. And the two intermediate scenarios have quite the same evolution. Perhaps it seems like the 4.5 scenario stabilizes at a lower level. And of course, the worst scenario keeps going up without any stabilization pattern by the end of the century. And one other thing I did then was to, so this is on the global level, but of course, humans and human activities are mostly located on land. So I've loaded here a land mask to study those evolutions, but using only data located on land. So with this function, I just crop the netsdf data to using the land mask. So here's an example at a random date in order to check that that the crop was a success. And if I do the same analysis using data located on land, I obtain this graph, which shows that, so in dashed lines, this is the land temperatures, and the plain line are the one that we had before on the global level. And you can see that on land, on each scenario, the temperature seems to rise faster than on a global level. And so what we see from this section is that, well, indeed, we have clear increasing patterns in temperature in high emission scenarios. But as this is only a global level, it is still quite hard to understand what are the actual concrete implications for human societies, human activities, and so on. So this is why now, in the next section, I'm going to show the computation of two heat and drought indicators, which are more concrete and which allows us to have a more evocative view on the impacts of global warming. So the drought indicator is the maximum number every year of consecutive dry days. And this T90P indicator is the number of days in a year where the daily temperature is above the 90th percentile of a reference period. So as you can understand, this time we're going to use daily data. And our reference period is the one I've mentioned at the beginning of the tutorial, the 1915-1999 period. And we're going to compare it to climatologies covering the 2026-2100 period. So same thing as before, we are using EarthKit and climate data request files to retrieve the data. As this is daily data, this will take probably a few minutes per file per data set to retrieve. So once again, I'm going to show them to you without actually executing the cells. So this time our dataset have exactly the same structure with those variables that we have to drop, and this time we have precipitation and temperature data. So we do also some pre-processing on the precipitation to go from precipitation flux in kilograms per square meter per second to total precipitation in millimeters. Well, in millimeters, because this is the unit with which computing the indicators is the most convenient. So here, with this pre-processing, we have our total precipitation variable. And those functions allow us to compute indicators, so the consecutive dry days and the T90P using the historical data as reference, and the other, and we are computing these indicators on the 4 scenarios. So this is a computation of the consecutive dry days in the historical data. Here is the T90P climatology for the historical period. And now, the first comparison, we're going to compute the indicators on the RCP 8.5 scenario, which is the worst case scenario, if you remember. So once again, retrieving the data, doing the pre-processing, computing the indicators. So this is the consecutive dry days. And now we're going to draw several maps of comparison. So RCP 8.5 versus historical reference data. So all those cells are meant to draw the map. And so in this first row is dedicated to the consecutive dry day indicators. So you can see that under the RCP 8.5 scenario, there are several areas that have very, very long droughts every year. I mean, it's an average, but you can see that in, well, of course, in this near Saharan there's desert, but also in Australia, Southern Africa, or here near the Amazon, which suffer from droughts. And here's the evolution from the historical reference period. You can see that in populated areas like here, the Mediterranean region, or here, Central to North America, you can see that the droughts are more intense than in the reference period, with a sharp increase in the number of consecutive dry days. But it is not homogeneously distributed. Whereas when it comes to the frequency of very hot days, it is clear that under the RCP 8.5 scenarios, they increase all over the world, but especially here around the equator, which seem very much hotter than either reference period. And the second comparison that we are going we're going to make in this notebook. So I will see that I'm almost out of time, so I'll try to make this quite brief. It's to compare it to a mitigated climate, so the RCP 2.6. So basically, we're going to do exactly the same computations, so T9TP and consecutive dry days, and draw the same maps here. So here is a comparison of consecutive dry days between RCP 8.5 and RCP 2.6. And you can see that here in the area we had spotted before, the droughts are much less intense under the mitigated scenario. So judging from the hint here, probably like 25 to 50% less intense, for instance. And here for the frequency of very hot days, you can see that well, there is much less stress here on the equator than with the RCP 8.5. And when you compare the two, you can see that on the entire planet, the frequency of very hot days has decreased by a large number, by a large percentage. So this shows that, well, actions made to mitigate climate can have a real concrete influence. And so this shows the importance of the mitigation efforts for global warming and climate change. So we're reaching the end of this notebook. So there are a few exercises that you can do if you're doing this notebook at home, such as, well, trying to analyze the evolution of trends in temperatures on the ocean, for instance. We provided a mask for that. Trying to compare those maps with other scenarios, so 4.5 or 6.0. Use other extreme indicators, so other than consecutive dry days or T9TP. Use other variables from the ECMWF. And you can also, focus your analysis on particular climate regions which are available. You can probably find a shapefile for them here. Those regions have been designed by the IPCC, or the Intergovernmental Panel on Climate Change. So you can also crop the datasets to such region to have a more focused area to study. Well, this is the end of my presentation. I hope you enjoyed it, and feel free to ask me questions if you have some. Thank you very much.
Thanks a lot, Alexandre, for the nice tutorial. It was really interesting, and obviously we have a few questions for you. So we will go to that part. The first one being, so you used your Earthkit during your tutorial. Is Earthkit reliable for analysis and detection of burn areas generated using Sentinel-2 images?
Well, I don't think Sentinel-2 is available using Earthkit. I think Earthkit is only dedicated to ECMWF data. I don't think that includes Sentinel-2.
Yeah, I would have also said it was for weather data and that type of thing, but maybe to be checked on internet. But yeah, I agree with you. Okay. Next question. Are the climate projection calculations done using an ensemble of climate models or a single specific model?
In this case, I've selected one single specific model. So if you visit or if you try to download from WEkEO, you can see that it will propose you several different models. So I've chosen one quite arbitrarily, but there are a lot of them to choose from.
Okay, thanks a lot for the clarification. Next question. How would you go about downscaling climate projections so they more accurately represent local climate change?
Well,
open question.
Yeah, well, I've quite mentioned at the end of the tutorial that you could always scrub the datasets to well, climate regions that were defined by the IPCC. So this is, I mean, those are each region has quite a typical climate, like Southeast Asia, Mediterranean, or the Amazon area. So would probably do a separate analysis for each of this region, which I'm interested in, to have like more local views on the impacts of climate change.
Okay, thanks a lot.
And for example, for the Mediterranean, the impacts of the droughts, it's quite higher and it's quite, well, significantly different than in, I don't know, Southeast Asia, for example. And that's quite obvious to check. Yeah.
Okay, thanks a lot. A question about the type of files you used. Why using JSON instead of netcdf file? Is the JSON faster to download than netcdf, or what's more important?
Okay, I don't. Perhaps I wasn't very clear when I explained that. So the JSON files are only request files. They only contain the request to the WEkEO platform. But when executing the either the HDA API or EarthKit, it's a netcdf that will be downloaded.
Okay.
So
Okay,
JSON
thanks.
contains only the request to the netcdf, which is downloaded for the notebook.
Okay. Okay, thanks. Another question, more about the beginning of the notebooks. The acronyms for the parameters are hard to comprehend. Is there a place where the complete name is shown?
Well, there are several acronyms. I'm not sure which one you're talking about. If it's about the climate indicators like CDD, which is consecutive dry days, and T90P, which is the frequency of days where the temperature is above the 90th percentile of the reference period. So those are taken from there is a dedicated article which lists lots of extreme weather indicators. So I've taken those acronyms from that page. There is a link in the notebook if you want to visit it and well, have more details about them. And yeah, probably I was for the RCP scenario, for instance, so representative concentration pathways. It's true that I've only mentioned it like once in the beginning of the tutorial and then not again. So perhaps it was also confusing. I'm sorry about that.
Thanks a lot for the clarification. So we will do a few more questions. This one. When you store data directly in variable on the Jupyter Lab, how maximum memory can you use?
I don't know the exact number. Perhaps that's more for the user support. I know that I tried to delete the variables when I've done using them because with climate data, the files are usually pretty big. So in order to save space, I try to do it, but I don't know exactly the number of the memory size that we are allowed in WEkEO.
I don't know. I don't know either actually, but I think we can find an article. I will check. I will put the question on the side. Okay, a general question. How much time does it take to execute all the code you showed?
Well, what takes the most time is the retrieving of the data sets. For the daily data, at the end, each earthquake request can take I don't know, 2 to 3 minutes. So I don't know if you do a run all on the notebook, perhaps it would take I don't know, 20 minutes, I would guess. Because the other processing is quite quick. It's mainly the data retrieving that causes trouble.
Okay, thanks a lot. So we have time for, I think, 3 more questions. Why did you use CMAP5 instead of a more recent data like CMAP6 or CMAP7?
I've used this one because this was the couple intercomparison model available on the WEkEO platform, but I'm aware that there are more recent ones.
Okay, thanks. Yeah, so we
But
have to update.
yeah, I think CMIP5 is the only one available on WEkEO for now.
Yeah, a few updates are still needed on the data catalog. Is your working environment on WEkEO GPU?
I'm using the WEkEO Jupyter Lab, using the Earth observation tools. So I think I'm using the basic WEkEO installation.
Okay, thanks a lot. So we will have time for one more question, I think. Why did you use both precipitation and temperature for the daily data, but only include temperature in the monthly data?
Yes, in the section where I was using monthly data, I was only using at the global evolution of temperatures. So I only needed to retrieve temperature data. And in the section where I use daily data, I wanted to compute drought and extreme heat indicators. And in order to compute the consecutive dry days indicator, I had to use precipitation data because a dry day in this indicator is defined as a day where the total precipitation is under 1 millimeter. So this is why I needed the precipitation data and the temperature data to compute the very hot days indicator.
Okay, thanks a lot for the explanation. So we will have to stop there for the question about the notebooks.